So, hello, I am Arpit. I am a PhD scholar and a Prime Minister Research Fellow under Professor I. Palani sir in Mechatronics and Instrumentation Lab. And I have with me Mr. Krishnapal Tomar. He is a PhD scholar. So, we are working on the concept of micro 3D printing. So, today we would be discussing about the principles of micro 3D printing, how it happens, and how it can be utilized in different applications, specifically focusing towards micro robotics application. That is where the course is beautifully designed for. So, before starting the underlying principle of micro 3D printing, as you might have understood in your classes, that is about there are two basic principles. One is additive process, and second one is subtractive process. So, in the additive process, normally what we do is we do the layer by layer deposition of the material, whereas in the subtractive process, the conventional lithography process or the etching process, what we normally say, is kind of into utilization. So, the additive process that is conventionally present in the market, in which wherein we do layer by layer addition of the material, it normally follows that the minimum feature size that we get will always be in range. It might be because of the complexity of the process, it might be because of the feedstock that is being fed. So normally in the additive manufacturing process, the feedstock that we feed is either in the kind of wire or it can be in the kind of some powders. Whereas what we are discussing today is the principle of laser micro 3D printing, in which the feedstock for the first time is being used in the form of a thin film. So thin film as a feedstock with a thickness of in some microns range, once it gets transferred, so the microns range whatever we have, let's suppose if we have a thickness of say 4 or 5 microns, then based on the experimental analysis what currently we have observed is that the transfer of the material, once it happens from the top surface to the bottom surface, which we would be discussing in detail, like what is the top surface, what is the bottom surface. So the transfer efficiency what we have observed is somewhere in the range of 70 to 80%, which means that if the thickness is somewhere around 5 microns, the material transfer would be around in the range of 3.4 to 3.7 microns. So that is what is conventionally being, or that is what we have observed based on the experimental output. Okay. So what it is used for? It is used for basically printing of different kinds of sensors, for printing of different kinds of materials. So as far as our experimental understanding is concerned, so there is a lot amount of materials that we have explored. Like we have explored pure materials such as aluminium. Then we have explored compound, or we have explored alloy such as shape memory alloy like nickel titanium. Then we have moved towards exploring ceramics such as zinc oxide, and now we are exploring its feasibility towards printing silicon carbide. So that is where the ranges of material. So a low range, a low dense material, and a high dense material. So like various ranges of material have been tried and printed, and they have been successfully printed. So I would like to just show you a simple use case. So if you could see over here, so basically this is the strain gauge. So this is that strain gauge that we have printed. So this strain gauge what you are seeing over here, it's a nickel titanium based strain gauge. So we have printed it in a specific shape, and then we have connected it with copper wires, and then we have tried and tested its gauge factor. So we tried to analyze, like with the commercial available strain gauges, how it is comparable and how much gauge factor are we getting. So this is just a use case that we have used. Then if we talk about the fine feature size, so the controllability of the system is also very important. And in our case, because what we are using is a laser printing, so because the laser hits the surface, the material ejects out, and since it moves on a XYZ stage, so it is an automatic translation stage. So once the material transfers, so the feature size what we can get is, so normally the gap that we can get between two lines, it can be in some microns, that is 5 to 10 microns. Whereas if we talk about the thickness, so a single layer of thickness, as I discussed, it depends upon the thickness of the donor material, and once it transfers onto the surface, how much is the efficiency that we have discussed. So we will be seeing it in detail. So what are the steps that are followed, then followed by the conventional principle that it is taking care of. So first, if I talk about the conventional principle, so I'm adding a video that will show you how the transfer of the material happens. So what is the underlying principle? So the underlying principle is that we have step one. The step one is what we are taking is a donor material. So the donor material what we take depends upon the laser that we are using. So in our case, what we are using is a 10.6 micrometer carbon dioxide laser. So the 10.6 micrometer laser, it should be transparent to the donor material. So the donor material what we are using is a silicon wafer. Silicon wafer we have taken because as the laser falls on the surface, as you might have understood in this course also, then normally once the light falls on the surface, it might get reflected, it might get transmitted, or it might get absorbed on the surface. Okay, so these are the three conventional principles that follows. So as the laser energy falls on the surface, what we want? We want that the maximum energy should transmit from the surface. It should neither get absorbed nor it should get reflected. Now as we move to the second layer is a sacrificial layer. So sacrificial layer, what do we do over here? So in order to create this sacrificial layer, we do a coating of a polymer. So in our case, what we use is a PDMS polymer. Okay. So PDMS polymer, why we have selected? Because this PDMS polymer, it is the wavelength of light, the 10.6 micrometer wavelength of light that comes, as it gets transparent from this surface, it goes into the second layer. The second layer what we have coated is a PDMS polymer, and this wavelength of light gets absorbed in this PDMS polymer. So why PDMS is selected? Because it absorbs this specific wavelength of light. So as it absorbs this wavelength of light, what it will do? It will create some gas pressure over here. Now below this is the third layer. The third layer is the donor material that we want to transfer. Okay, so whatever material, as I told initially also, like we have explored with pure materials such as aluminium, then we have used nickel titanium, then we have used zinc oxide, silicon carbide, and other ranges of material. So the third layer what we are talking about is that layer. So that third layer, once we are coating it onto the surface, then as the laser falls on the surface, from first layer it gets transferred to the second layer. The second layer, it creates a gas pressure. This gas pressure has to release because it creates some kind of instability in the second layer. Now the gas pressure, in either for it to release, it might have to either go onto the front side of it or it might go on the back side of it. Now the back side of it, what we are seeing is a solid silicon substrate. So it won't allow the gas pressure to go on the back side. So what will happen? The gas pressure will automatically have to come on the front side. The front side of it is what? It's a coated thin film. So this thin film won't hold that gas pressure because that gas pressure is very high. So it won't hold that gas pressure. So it will eject the material from the surface. The material, once it ejects from the surface, it comes onto the base substrate. So the base material is the acceptor substrate. So as you have seen in this case, so this is a flexible PET substrate. So this is a flexible PET substrate wherein what we observe that the material transfers and it comes onto this flexible PET substrate. Now this does not mean that the technology is only focusing on the flexible substrate. We can even do these kinds of printing on the solid substrate. So like if you see in this case, so if you see in this case, so this is a solid silicon substrate. Now on the solid silicon substrate, if you will see, this is a beautiful hexagonal shape that is being printed. So the beautiful hexagonal shape that is being printed is on the solid substrate. So that means that the technology does not depend upon the acceptor substrate. The technology does not depend upon what acceptor substrate we are using. It can be any substrate. It can be a solid substrate as well as it can be a flexible substrate. Okay, so this is the underlying principle. There would be there would be animation that would be going wherein it would be showing how the material transfer is happening. Now what we are going to do is we are going to understand the basic principle. After the principle, we are going to move towards step-by-step process. How do we do it? Okay, so that is very much important for you to understand. Like how do we do it? Okay, so we move to the first step. So the first step, as I said, what we need a silicon wafer. Okay, so step one is taking this silicon wafer. Okay, so this is that silicon wafer that we have taken. Now what we will do is we will coat a PDMS layer on it. The PDMS layer has to be coated. Okay, now this also requires optimization because does not mean that any thickness of PDMS will work for our case. No, because what happens as the laser falls from the back side of it and it's transferred onto the second layer, that is the sacrificial layer, the laser energy and optimization is done in a way that the gas pressure is optimum enough to eject the material because that laser energy should not interact with the third layer of the material. So we have to maintain that optimized thickness. Why for? Because if the thickness is less, what will happen? As the laser hits the surface, it will just tear off the sacrificial layer and it will interact with the material, which means that the material property will get changed, which we do not want. So what we want? We only want that the material should eject out from the surface, and it should never happen that some amount of material comes out or the laser interaction with the material happens. If in any case the thickness of the PDMS layer is very high or it is more, then what will happen? Then the laser energy, once it hits the surface, it won't generate the sufficient amount of pressure that is required because of the resistance of the material. So it won't allow the gas pressure that would form, it won't allow the material to eject out. Or what we have also observed while doing experimentation, that at time PDMS also comes out from the surface and some white layer is formed along the transferred material. So why does that happen? It happens because of the excess PDMS thickness. Okay, so we have to optimize that thickness. Okay, so what we conventionally do, so the simple principle is we take this silicon wafer, we put it on a spin coater, and which is a vacuum based spin coater, and on the top of it we put 1 or 2 drops of PDMS. The PDMS ratio that we use is 10:1. That is the ratio that we use. PDMS A is to PDMS B. So normally the PDMS polymer that is being used, so it has a main solution and a binder. So the solution to the binder ratio is 10:1 that we conventionally follow. But of course, it can also vary. People use 8:1, 6:1 to 14:1 also, depending upon the application that they have been working on. So we use 10:1. Okay. So we do a spin coating. So the spin coating, of course, again it is optimized. So we normally do it in the range of 5000 RPMs to 8000 RPM for 100 seconds. So 100 seconds comprises of the acceleration time of 10 seconds, the deceleration time of 10 seconds, and a holding time of 80 seconds. And then we do the spin coating. So the material is then spin coated and then it is present on the surface. Then what we do, the next step, once this material is spin coated with a sacrificial layer, what we do is we keep this on a, we give heat to it. Okay, so it's like 80 to 100 degrees of heating, and that is done by keeping it on a hot plate. Okay, it can be done in an oven as well, so that does not it is not really binding that you use a heater only. It can be done anywhere, but it has to be given the temperature of 80 to 100 degrees Celsius just for the curing of the PDMS layer. So normally if you don't have a heater, you can keep it in the atmosphere, open atmosphere, but the time taken would be more because it would just take heat from the atmosphere, and the atmospheric heat would be around 30-40 degrees depending upon the place where you are living. So it would vary from place to place. So appropriately then it will take time to dry, or it will take time to cure. So what we do an accelerated heating, and based on that heating the curing happens. Okay, now once the curing happens on the surface, now what we say that this surface is ready for going for the third process. So what is the third process? The first process is selection of the wafer. The second process is coating of the sacrificial layer, and now we move on to the third process. What is the third process? Third process is coating the material, the donor material that we want to coat. Okay, so how do we do that coating of the material? So the coating of the material follows using the principle of sputtering. Okay, so you might have understood in the past lectures about other deposition techniques such as E-beam technique and flash evaporation. Now we are going towards the next process, that is sputtering. Okay, so the third step that we are discussing about is sputtering. Okay, so sputtering, why do we do? So sputtering is done to create the third layer, the sacrificial, the third material layer or the donor material that we want to transfer. Okay, now as we have also discussed, like initially also as I told, that different ranges of material has been explored in this technique. So like if I show you, what do we require in this case? So as in the discussion, you might have understood in the E-beam deposition or in the flash deposition that we require some wires, or we require some pellets in order to do the deposition of the material. In this case, we don't require anything as such. What we require is a target. Okay, so this is a target material. So what I have in my hand is a silicon carbide target. Different material targets are commercially available in the market, so that you can use. So like in this case, what you see, this is the TiO2 target. TiO2 is titanium oxide target with a copper backing. So both of them will have a copper backing. Okay, so copper backing plate is given because normally with the oxides, they don't have that conductivity, so it becomes a challenge. So in order to take care of that conductivity issues, what we do a backing of the copper plate. Okay, so copper plate allows that conductivity, the sufficient conductivity that we require. Okay, so this is the target that we require in this case. Now, what happens? So if I give a basic understanding or a basic principle of sputtering, so everyone might have of you have tried plucking a mango from a tree. Okay. So what do we do? The conventional process is we take a stone and then we throw it on the mango that is there. So what do we do? We have a mango that is lying on the tree. The mango has some amount of mass. Okay. Since it has some amount of mass, it does not have that velocity. Okay. What you do? You take a stone and you throw it on that mango. What you are doing? You have a stone in your hand. Now that stone has a mass and it has a, and once you are throwing it onto the mango side, it has some velocity. Okay. So now this mass into velocity is momentum. Okay. Now as it hits the mango that is there on the tree, so it will take that momentum. Now it has that mass. What it will do? It will take the velocity. Okay. It will take the velocity and it will come from the surface. That is the principle of momentum transfer. The momentum transfers from the stone to the mango that is lying there and it comes down onto the surface, on the base surface. Okay. So that is how it happens. So here also the similar principle follows. What happens in this case? So in this case, it is basically DC or RF. It's like direct current or radio frequency. So there is a positive biasing and there is a negative biasing that you might have read in your class also. So what we normally do, we give that amount of energy to it. So this is a complete vacuum chamber. This is complete a vacuum chamber. It works in vacuum environment. So in order to create vacuum, what do we have? So we have a rotary pump, which creates the basic vacuum up to 10 to the power minus 3 millibar, and then in order to take it higher, up to 10 to the power minus 5 or even higher. So what we use is a turbo pump. Okay. So normally in our E-beam or in flash deposition, we use diffusion pump, whereas in this case we use turbo pump, TP. Okay. So this has a turbo pump. Okay. So turbo pump, it can take to even lower 10 to the power minus 6 millibars also. Okay. So what we do as we create this vacuum. Okay. So you see this is the surface. Okay. So here we place our sample. Okay. And then this, what you are seeing over here, this is a substrate heater. So we can do substrate heating, as well as whatever we are seeing over here is a rotator. So it will rotate the sample continuously. So the sample that would be placed over here, that would continuously be rotating in order to get a uniform deposition on the surface. Okay. So this will have a rotator unit. Okay. Now this is the target. This is what we call it as a gun. This is the gun. Okay. And on the gun we put our target over here. So the material that we have to deposit. Okay. So we put the material, then the target that you have seen. So basically the target that I have showed, we are putting it over here. Okay. Now once you give that energy, what will happen? The electrons or the material, the atoms that is present on the surface, they are excited and they want to come out of the surface, but they can't come out from the surface. What we have to do in order for the material to come out from the surface? As I told you, the case of mango tree. Okay. So you have to throw a stone on the mango tree for the momentum to transfer. So in this case, what we do? So we purge argon. What do we do? We purge argon gas. Now the argon gas is connected. So this is a MFC. MFC is mean flow control. So it allows the material, the argon in the controlled manner, whatever control we want. So how much centimeter cube of argon we need to feed. So we can control it, and as the argon flows onto the surface, as the argon flows from here, so this chamber will have some amount of argon. Now this argon, what will happen? So this argon will act as those stones. Why we have used argon? Because argon is it's a noble gas. It means it is non-reactive in nature and it has some mass also. Okay. So it won't allow any reaction to happen. If you are feeding other gases, suppose oxygen you are feeding, then it might form oxide. If you are feeding nitrogen, it might form nitrites. Okay. We don't want that. So what we will do? We will feed argon gas. Now the argon, once it comes into this chamber, so this argon will act as a stone and this argon will come and it will strike the surface. Okay. So as the argon strike the surface, it will eject the material from there and the material will go out. The material will go out and it will start getting collected on the substrate material that we have created. Okay. So the material, that is the silicon wafer, this coated silicon wafer. So this we will place, and the material, whatever material, suppose silicon carbide you are using, so the silicon carbide will come out and it will slowly get deposited. It will be like atom by atom deposition. So the atom by atom deposition will happen on the surface, and then appropriately we get thickness. Now this also depends upon the material that you are using, which means that it is not a standard procedure that for this amount of time if you are doing, then you will get this amount of thickness, because it again depends on material. For instance, if you are taking aluminum, so or if you are taking metals such as nickel, titanium, so it takes 15-20 minutes to get a thickness of 3 to 4 microns of thickness. But if you are going for silicon carbide is a very tough material, so it at times require 10 to 12 hours in order to get a thickness of 3 to 4 microns. So we do it in steps to get that amount of thickness. Okay, so it again depends upon which material you are going to work with, and then appropriately you do the deposition, layer by layer deposition, or it like atom by atom deposition, and then slowly you will get the thickness. Okay, so if you see it in the video that we have attached, so that is how you are seeing that a plume is coming or a plasma is coming. So you are seeing this pink color plasma that you are observing. So this is that plasma zone in which that material is ejecting from the donor, from the target, and then it is coming out and slowly getting deposited on the top surface, which is continuously rotating. So the material comes out and slowly it's get deposited over here. So it's like atom by atom deposition, and because it is atom by atom deposition, it means it gives certain advantages. What advantages give? The first advantage is the controllability is in your hand. It's very much controllable. If we compare it with the flash deposition technique, where the material just flashes off and gets deposited, the controllability is not there. Whereas in this case, you will get good amount of controllability that you require for your case. Okay. Then the second advantage is, since the material gets deposited atom by atom, the uniformity will be very good. Okay, and since you are also rotating the sample at the same time giving a substrate heating on the surface, it means the rotation and the substrate heating induces a uniformity. And since atom by atom material is going, so it will be very uniformly distributed all along the material, which means you can expect that uniformity to be maintained, which is not in case of say flash deposition. But again, in order to achieve that thickness, the time taken would be higher. Time taken would be very high. So it depends upon the material that you are going to work with. Okay. So apart from the standard process of forming vacuum and the time taken in order to form vacuum, the third step, which is the material deposition, it will take more amount of time when compared with the other technologies of deposition that is being used. But this is one very famous and a very conventionally used technology. So sputtering is very much into utilization. So DC sputtering, we use it normally for metals, and RF sputtering normally for oxides like titanium oxide or silicon carbide or zinc oxide. Okay, so that is how we do the material by material coating. Okay, or layer by layer. Now once we have done this complete coating, now what we do? So we have this substrate, or we have this top material which has these three layers. The first is the donor, followed by the sacrificial layer, followed by the donor material. So this is ready. Now we need an acceptor. So as we have discussed at first place also, that acceptor that you are going to use, it can be anything. It can be flexible acceptor, it can be solid acceptor. Okay, because what is happening, the laser only hits the surface, goes to the second layer, creates a gas pressure. Till that point only that laser work is there. Now the material, once it's ejected out from the surface, it transfers onto the third layer. It transfers onto the acceptor substrate. So acceptor substrate, as we have discussed, it can be a solid substrate, as in this case a silicon wafer on which a different beautiful shapes are printed. It can be a solid substrate, or it can be a flexible substrate, as we have discussed in starting also. So if you see this, so basically this is a solid substrate, so on which this shape is being formed. So this is a solid silicon substrate. You can do it on a ITO coated glass or a normal glass or any other solid substrate also, because the laser interaction is only happening between the first layer and the second layer. Now the third layer, only because of the gas pressure, the material is getting transferred. So since the material is getting transferred, so any kind of acceptor substrate can be used in that case. But one important thing that you have to take care is that while doing the transfer on the substrate, because the material, once it's transferred from the surface and comes onto the base substrate, it has to adhere to the surface. So for adhesion of the surface, what is happening? The phenomena that is happening over there is called as local welding. Because the material, once it's transferred, it comes onto the substrate, so it has to weld on the surface, or it has to join the surface for it to have a kind of good amount of flexibility. At the same time, the strength of the sensor that is being formed should also be intact. So to create that local welding on the surface, what we do substrate heating. So doing transfer, the acceptor substrate is heated. So once the acceptor substrate is heated, the material comes out in pixelated form and it's transferred on the surface, and it gets attached to the surface. So due to that, a good amount or a good strength of the sensor is being formed, like I'll show you in this case. So in this case, if you will see, so basically the material that was transferred, it is very much intact on the surface. It is very much intact on the surface, and it won't come out from the surface. It won't come out, okay? Because a good substrate heating is given onto this surface, okay? Similar case you have observed in this case also. So similar case you will observe in case of a strain gauge also. So the strain gauge that we have formed, so there also the material, if you are bending this strain gauge,
in whatever bending you are doing, the material will not come out from the surface. Why it will not come out from the surface? Because the substrate heating is given. Now this technology, apart from this kind of printing, it also gives a window of printing different shapes. Okay, so because it has these motion stages of XYZ stage, so what you have to do, you have to just feed that G code and M code. Okay, so G code and M code, and then whatever shape you want to print, you can just give that code appropriately, so it can print. So it can print like gear shapes, it can print multiple flexible antennas, or it can print say strain gauges, or it can even print interdigitated structures. So a lot amount of structures, a lot amount of sensors that are being used in electronics industry or microelectronics industry, that can be done. Now one also there is one more thing that we are also tapping is, like normally if we see the electronics, the microelectronics that people have been working towards, so what happens is that the conventional process of forming a PCB, so in that PCB is formed and is under utilization. But at times it happens that because the material that is being joined, at times it gets damaged from between. So since it is getting damaged from between, there isn't any technology as such which will improve that which will bind it again, and then that sensor can be utilized again. Okay, so or that electronics can be utilized again. So if there is some damage that happens in the fabricated sensor, so that has to be thrown, which means that the electronic waste is getting generated. So what can be done? If we have something in localized region, if we can do something, then that solution, that problem can be solved. And this can be one of the technique in which, suppose if a printed PCB is damaged from between, so wherever there is a damage, you transfer the material in that specific zone and to align that material in a way that it joins completely, and then try to utilize that sensor again. So this is one probable way which the probable window that this technology opens. So this is an additive based technology, a micro additive technology, in which wherein by microns layer of transfer in a layered by layered fashion, we can fabricate micro sensors, and these micro sensors can be utilized for different applications, such as in micro robotics application, as you are taking in this course. Okay, so this is about the overall understanding about this. So we would be also adding certain videos, certain shapes that you would see in the upcoming slides or in this complete video, and you will get a better understanding about this technology. Thank you.